When was the last time you questioned a maintenance schedule? And I don't mean just, glancing at a calendar on the wall and sighing because a due date is coming up.
Right, like dreading the work order.
Exactly. I mean, genuinely questioning the fundamental logic of it. Because if you picture a typical factory floor or, a massive processing facility you've maybe worked in or walked through.
Oh yeah, they're everywhere.
Yeah, you see these experienced technicians out there taking these complex, perfectly functioning machines apart every single month. I mean, they're unbolting flanges, replacing seals, draining fluids.
Taking it down to the bare metal, basically.
Right. And they're doing all this heavy, really intrusive work simply because a spreadsheet generated a work order, not because the machine was running hot or vibrating or drawing too much amperage.
It's just because 30 days happened to pass since the last time they turned a wrench on it?
Exactly. So welcome to this deep dive. Today we are tearing into a massive stack of operational and reliability engineering sources that honestly completely shatter how most of us think about maintenance.
It's pretty wild stuff. We're looking at research from NIST, the National Institute of Standards and Technology, plus those landmark sub-MEPP studies from the U.S. Navy submarine fleet.
Yeah, and the Nallen and Heap report from commercial aviation, the NASA guidelines on reliability-centered maintenance, and just a huge trove of CMMS data from across the industry.
The overarching mission for today's deep dive is to really understand why routine maintenance so often, devolves into pure waste.
Right.
And the core premise weaving through all these sources is this idea that maintenance becomes waste when the schedule survives longer than the reason the schedule was actually created.
That is such a good way to phrase it. And we're going to explore why 85% of equipment failures just, well, they don't care about your calendar.
They really don't. And we'll unpack why 68% of failures follow this thing called an infant mortality curve.
Which is a terrifying number, honestly. And, we'll talk about how you can transition a team away from this habit-driven or even superstitious maintenance towards something based on actual evidence.
I love that you use the word superstitious, because that's exactly what it is. Most of us operate under this deep-seated psychological bias that action inherently equals perfection.
Right, like if I'm doing something, I must be helping.
Exactly. We feel productive out on the floor, tearing things apart. We feel safe. But mathematically speaking, the reality is a lot darker.
Yeah, because the sources pose this really uncomfortable question. What if the very act of maintaining equipment is actually the leading cause of its failure?
Which just sounds so backward at first, because the traditional mindset, it assumes physical things just wear out on a completely predictable timeline.
Yeah, like if the manufacturer says a part lasts a year and you swap it out at 11 months, you feel like a genius. You dodge the bullet.
It feels like common sense. We project our own biology onto it, like we age and degrade, so machines must do the exact same thing.
Oh, totally. I catch myself doing this, in my own life. I'll go change the oil in my car.
Yeah.
Just because the little window sticker says it's time.
Even if you've barely driven it.
Right. Like if it's just been sitting in a climate-controlled garage for 8 months, there's just this voice whispering that it is always safer to replace things before they break.
Well, and before the 1960s, the entire industrial world basically ran on that biological assumption. Everything was built around fixed, time-directed overhauls.
Just reset the clock to zero.
Exactly. Run it for a set number of hours, tear it down, rebuild it. But as systems started getting exponentially more complex, especially in aviation and the military, they started noticing this massive, terrifying disconnect in their data.
And when you're flying commercial airliners or operating nuclear submarines, failure isn't just a little downtime, it's a catastrophic loss of life. You cannot afford to operate on superstition.
The stakes were just too high. So in the 60s and 70s, aircraft were getting massive. The Boeing 747 was kind of the tipping point here.
Because you couldn't just tear down a 747 every few months.
Right. The airlines realized if they kept doing strict time-based overhauls on these massive jets, the planes would spend more time in the hangar than in the air. They'd go bankrupt.
So they actually started looking at the failure data instead of just guessing.
Yeah, the industry, backed by the FAA, got two researchers at United Airlines, F. Stanley Nallen and Howard F. Heap, to analyze this. And in 1978, they published a report that basically upended the entire engineering world.
And it wasn't just aviation that found this out, right? I was looking at the U.S. Navy data from the late 90s, their submarine fleet.
The sub-MEPP studies, right?
Yeah. And a submarine is, what, the most unforgiving environment on Earth. Extreme pressure, salt water, complex life support. And the Navy arrived at the exact same conclusion as the airlines.
Rigidly planned, time-based maintenance did not improve asset performance. In fact, aggressive calendar replacements were often making things less reliable.
Okay, so let's unpack why that is. Because Nallen and Heap, and later the Navy, they mapped out the physical degradation of components into 6 distinct mathematical curves.
This is where the math really dismantles the calendar. It completely changes your mental model.
Let's break them down. But let's avoid just reading them like a list. I want to really understand the physical mechanics here. Let's start with the bathtub curve, since that's the one that matches our everyday intuition.
So the bathtub curve, on a graph of failure probability over time, looks exactly like a cross-section of a bathtub.
Right, it dips down, goes flat, and then goes back up.
Exactly. You start with a high probability of failure right at the beginning. This is infant mortality. Physically, this could be a casting defect in a metal housing or maybe a weak solder joint on a circuit board.
Like the classic cheap toaster phenomenon. If it's wired wrong at the factory, it smokes and dies on day 2.
Yeah, but if it survives that early stress, the failure rate plunges. That's the flat bottom of the tub. The machine just hums along for its intended lifespan.
Until it hits the wear-out zone.
Right. At the far right of the graph, the curve spikes sharply up again. The physical materials just give out. Gear teeth grind past tolerance. Seals get brittle.
And that feels so right. That's how we think everything works. But the Nallen and Heap data shows that only 4% of equipment actually follows this pattern.
4%. It's incredibly rare. Now, closely related to it is the pure wear-out curve, which is about 2%.
And that's basically the bathtub without the infant mortality at the start.
It's spot on. Probability of failure stays low and flat from day 1 and then sharply spikes at the very end of its useful life.
So this would be things designed to be consumed, I guess, like brake pads or tire tread.
Yes, exactly. They predictably wear away with use. But if you combine the bathtub and wear-out curves, that's still only 6% of total failures.
Wow. Okay, so what's next? So let's just talk about the fatigue curve, which is about 5%.
Right, the fatigue curve. Unlike the bathtub, there's no long, stable period here. The risk of failure is just constantly, gradually climbing from the moment you turn the machine on.
What does that look like physically? Just continuous stress.
Think about metal fatigue. If you take a heavy steel spring and constantly compress it, every single cycle creates these microscopic fissures. The material gets more brittle.
So it's slightly more likely to snap on day 10 than day 9, and way more likely on day 100.
Exactly. It's a linear degradation. Now, pair that with the break-in curve, which sits at about 7%. This one is almost the inverse of fatigue over the long run.
Because it starts with a low risk, climbs as it breaks in, but then it just levels off, right?
Yeah, it hits a ceiling and settles into a constant risk for the rest of its life. You see this with complex mechanical assemblies, gears, meshing, bearings, seating under load.
The initial friction causes some wear, but once the surfaces kind of polish each other.
The degradation stops accelerating, it plateaus, the machine finds its equilibrium.
Okay, so if we tally all these up, bathtub, wear out, fatigue, and break-in, we've only accounted for 18% of all failures. We aren't even at 20% yet.
This is the turning point right here. 14% of failures follow what's called the random pattern.
And this curve is just a completely flat line.
Just horizontal. The probability of failure is exactly the same on day 1, day 500, and day 5,000. Age has absolutely nothing to do with it.
I always think of this like getting a nail in your car tire. The age of the tire doesn't dictate whether a roofing nail is on the highway when you drive by.
That's a perfect analogy. The puncture is random. Replacing a tire every 6 months just because it's 6 months old doesn't protect you from the nail.
It's just a massive waste of money.
And in a factory, imagine a massive pump in a wastewater plant. If a chunk of debris gets past a screen and hits the impeller, it shatters. It doesn't matter if you installed it yesterday or 3 years ago.
Right, the failure is driven by an external event, not metal fatigue. Which brings us to the absolute heavyweight champion of these curves.
The infant mortality curve.
68% of all equipment failures follow this one single curve. Let's just sit with that. 68%.
It's the data point that completely rewrote reliability engineering. This curve shows a massive spike in failure risk right at the start of a component's life or, and this is key, immediately following a maintenance overhaul.
But if it survives that initial dangerous period, it just drops to a steady low risk, right?
Yes, it never hits a distinct wear-out spike. It just runs steadily until some random event takes it out.
So, synthesizing this for someone running a plant. If you combine the curves, that are genuinely age-related, bathtub wear out, fatigue, you max out at maybe 11 to 15% of failure modes.
Leaving a massive 85 to 89% of all failures as completely random or driven by infant mortality.
That just makes the whole foundation of time-based maintenance completely collapse.
It really does. If almost 90% of failures have nothing to do with the age of the part, then tearing machines apart based on a calendar is mathematically unjustifiable. The calendar is actively lying to you.
Which leads to such a glaring question. Why are so many machines failing right at the beginning or right after a technician works on them? If wear out isn't killing them, what is?
Well, the dark secret of the maintenance industry is self-inflicted wounds.
Maintenance-induced failures.
Exactly. When a tech performs intrusive preventive maintenance on a calendar schedule, they are physically violating a sealed system. They're cracking flanges, exposing delicate internals to the environment.
And this is equipment that was probably running perfectly fine the day before.
Yes, it was stable.
Think about a house. If you move into a new house and the plumber forgot a seal, it'll leak in the first week. That's infant mortality. But if it doesn't leak for a month, it's probably good for decades.
It's proven itself, right?
But imagine if, for preventive maintenance, you ripped open the drywall every single year to install new pipes just to be safe. You aren't preventing leaks, you're just giving a new contractor a fresh chance to forget a seal.
That is exactly how intrusive industrial maintenance works. Every time you disassemble a healthy machine, you create fresh pathways for human error.
Let's walk through a real example, like taking apart a high-speed compressor.
Okay, so the technician unbolts the housing. Boom. Immediately, there is a risk of microscopic airborne dust entering the lube system. Even a few microns of dirt can score a bearing at 10,000 RPM.
And then they have to put it back together.
Right. Did they use the exact torque pattern? If they over-torque one side, they warp the housing. Did they pinch an O-ring? Did they use the right grease? Or just whatever was on the cart?
And the data from assertivity really hammers this home.
Yeah.
Human error is an inevitable statistical certainty. You can't train it away completely.
And the aviation safety research is particularly grim on this. An aircraft's accident or critical failure risk is 33.8% higher in the first hour following a scheduled inspection compared to its normal baseline.
That is wild. The plane is statistically in significantly more danger right after a team of highly trained mechanics has taken it apart to make sure it's safe.
It sounds so counterintuitive until you understand infant mortality. And the innovative research shows the same thing in manufacturing.
Right. They estimated that maintenance-induced failures account for anywhere from 30 to 55% of all breakdowns in certain plants.
There's one case study in the sources that I think is the ultimate smoking gun here. An offshore oil and gas platform in Western Australia.
Oh, I remember this. They audited their preventive maintenance and basically just slashed the schedule, right?
They cut their routine PM tasks by 25%. Just stopped doing a quarter of the work.
And the result wasn't a spike in breakdowns. It was a 25% reduction in corrective maintenance.
Yes. By simply refusing to touch the equipment, it got more reliable. They proved they were actively causing a quarter of their breakdowns by trying to prevent them.
I just want to push back on this so the implications are crystal clear. Are we genuinely saying that by following the manufacturer's manual, the binder that says replace every 6 months, we are actively sabotaging our own systems?
In many cases, yes. Because when a complex system has been running smoothly for 6 months, it has dynamically proven itself. It survived the infant mortality phase.
It proved it was installed right, the tolerances are good, the casting was solid.
It achieved stability. When you tear it down because the manual says so, you rip out a proven, battle-tested component and replace it with a shiny new, unknown variable from the storeroom.
A component that has a 68% chance of following an infant mortality curve.
Exactly. You artificially reset the clock on failure risk. You force the machine to survive its most dangerous period all over again.
You're trading a proven asset for an unknown variable. It's wild. So if the data is this overwhelming, why do incredibly smart engineers and plant managers keep doing it?
It comes down to organizational inertia. The sources have a great term for this. They call the modern workplace an assumption factory.
The assumption factory. That sounds like a really miserable place to work.
Well, it describes how these operational habits become practically immortal. When a new plant is built, engineers create a massive maintenance schedule based on manuals and educated guesses. It's an imperfect starting point.
But then, over the next 10 years, the reality of the plant completely changes. Production doubles, things get hotter. But the spreadsheet from year one never changes.
Exactly. The assumption remains active long after anyone stops validating it. The logic becomes entirely circular.
We always tear this pump apart every month, and the plant hasn't burned down, so tearing it apart must be what's keeping it from burning down.
Institutional superstition. And the financial cost of this is staggering. Think about a monthly intrusive inspection on a gearbox. Say it takes a tech 2 hours to lock it out, tear it down, inspect it, and clean up.
Okay, so 24 hours a year. Let's say the loaded labor rate is 85 bucks an hour. That's roughly $2,000 a year for one single task on one asset.
Right. Now, in a large facility, you might have 40 of those exact same gearboxes. Now you're burning $80,000 a year in sheer labor, plus the cost of gaskets, oil, seals, and downtime.
You're spending a small fortune on work that mathematically prevents absolutely nothing.
That is the overmaintenance trap. You bleed resources dry just to check a box in a software program.
And the worst part is, the overmaintenance trap directly causes the undermaintenance trap.
Because your techs are too busy doing useless teardowns to actually monitor the highly critical assets.
Exactly. And when a critical asset goes down in a continuous process industry like a paper mill, unplanned downtime can cost up to $260,000 per hour.
You're stepping over $100 bills to pick up pennies. And this bad data infects the supply chain, too. It creates what the sources call an MRO, mess maintenance, repair, and operations.
Because if the maintenance schedules are detached from reality, your storeroom becomes a hoarding nightmare.
Yeah, facilities end up carrying a 30 to 50% excess inventory.
There was that hilarious but painful example in the sources about the AC electrical contactor. They had the exact same part stocked under 3 different OEM part numbers.
Because the compressor manual called it Part X and the conveyor manual called it Part Y.
So they bought both, tripling carrying costs. And the nightmare scenario is the compressor dies at 2 a.m., they check for Part X, see it's out of stock, and pay a massive premium to fly one in overnight.
Meanwhile, the exact identical component is sitting 50 feet away in a bin labeled Part Y. It's pure systemic chaos.
It makes me think of that visual metaphor from the sources. Walking into a massive compressed air utility room. It's pristine. Compressors are cycling hard, cooling fans screaming. The whole system is aggressively engaged, burning immense energy.
And it's doing all of that just to compensate for one tiny overlooked air leak on a quick connect fitting in some forgotten corner of the plant.
Right. The system is sweating bullets to compensate for a failure to diagnose reality. That is a rigid, time-based PM schedule in a nutshell.
A massive bureaucracy of labor compensating for the fact that nobody has stopped to ask, why are we actually doing this?
Okay, so if I'm a manager listening to this, and I realize my facility is trapped in the assumption factory, how do I break the cycle?
Well, the sources outline a very pragmatic diagnostic tool. It's called the no-fault repetition check. It's beautifully simple.
How does it work?
You go into your CMMS, your maintenance software, and pick one recurring PM task completed at least 6 times in the last year. Open the work orders and count how many times the tech wrote "no defect found" or just checked the inspected satisfactory box.
And then you compare that against the actual breakdown history of the machine.
Exactly.
So what's a good baseline? What does a healthy, optimized program look like in the data?
The Forge Reliability Benchmark says an optimized program should have a PM finding rate of between 3% and 8%.
Wait, only 3 to 8%. So out of 100 scheduled inspections, I should only be finding an issue maybe 5 times.
Yes. That is the sweet spot of risk mitigation versus labor efficiency. If your finding rate is below 2%, it is a mathematical guarantee that you are wildly over-inspecting the equipment.
If a tech goes out 12 times a year and 12 times a year says looks fine, the task is useless. It's a pencil whipping exercise.
Precisely. So once you find these useless tasks, you use PM optimization, or PMO, to clean it up. The innovative research highlights 3 main approaches, depending on your data maturity.
Let's walk through those.
First is FRACUS-based PMO. That stands for Failure Reporting, Analysis, and Corrective Action System.
Sounds intense.
It is highly quantitative, requires really clean, disciplined CMMS data. You mine historical work orders and mathematically redesign schedules based on actual failure frequencies.
But that only works if your techs actually write detailed notes, right?
Right.
What if your historical data is garbage? Or what if you're in an industry where you can't afford to wait for failures to accumulate?
Then you use RCM-derived PMO, Reliability-Centered Maintenance. This is the heavy-duty framework pioneered by the airlines and NASA.
So it's not looking backward at history, it's looking forward.
Yes, it's a rigorous engineering analysis of every single way a component could fail and the consequences of that failure. It's incredibly resource intensive. You really only use it in safety critical industries like nuclear power.
Right, where one failure means absolute disaster. But for a normal manufacturing plant without a NASA budget,
They use judgment-based PMO. This is the most pragmatic starting point. It relies on the lived, tactile experience of the people on the floor.
you just get the senior techs and reliability guys in a room.
Pull up the schedule and ask the hardest question. Does this task actually make sense? You leverage their tribal knowledge to strip away the useless tasks immediately.
And the end goal of all three methods is what the sources call the kill the PM strategy.
Right. If a task produces 0 actionable findings over 12 months, you have 3 valid responses. Option 1, extend the interval. If monthly finds nothing, make it quarterly.
Option 2, simplify the task. Stop tearing the machine apart. Just do a visual inspection.
Or option 3, eliminate the task entirely. Just wipe it out.
And here is where we hit the wall of corporate reality.
Hmm.
If I'm a maintenance manager, I can't just stand up in a production meeting and say, hey, I'm deleting 20% of our PMs to save labor.
Oh, absolutely not. Management is too risk-averse.
Right, because if I cancel a PM on a motor and that motor randomly dies next week, the plant manager is going to say, it broke because you stopped doing the PM. It's career suicide.
It is the most common political hurdle in reliability engineering. But the experts offer a brilliant strategic maneuver for this. The safest kill is a substitution.
You frame it as an upgrade, not a cancellation.
Exactly. You don't walk in and say, I canceled the gearbox teardown. You say, we realized the monthly teardown was highly intrusive and risky. So we recovered 24 hours of labor by eliminating it and replaced it with a non-intrusive vibration monitoring route.
That gives us better fidelity on the asset's health anyway. That is corporate judo right there. You change the narrative to, we are doing something demonstrably smarter.
And you brief them on the dollar amounts recovered before they even process that the old task is gone.
Which perfectly sets up the ultimate goal here. Moving away from calendars entirely and transitioning to condition-based maintenance, or CBM.
To really understand CBM, we have to look at the NIST definitions. Preventive maintenance is scheduled by time or cycles. It's blind to the physical reality of the machine.
Right.
But predictive, or condition-based maintenance, is initiated exclusively by observed operating condition data. The physical reality of the asset mathematically justifies the intervention.
We swapped the wall calendar for diagnostic physics. But practically speaking, if we aren't unbolting covers, how are we looking inside?
The technologies are incredibly sophisticated now. The most prominent is vibration analysis. A tech puts an accelerometer on a bearing housing. It doesn't just feel shaking, it captures the whole frequency spectrum.
So if there's a microscopic pit on a ball bearing-like spalling,
Every time the ball rolls over that pit, it creates a specific high-frequency impact. The software detects that microscopic defect weeks before a human could ever hear it.
it's detecting the geometry of the failure before it's even a problem. What else do they use?
Thermal imaging, or thermography. Point an infrared camera at an electrical panel. A loose connection creates resistance, which creates heat. You see it long before it melts.
That's huge for fire prevention.
Then there's oil analysis tribology. You take a syringe of oil from a gearbox, send it to a lab, and they use spectrometry to look for microscopic metal particles. High levels of bronze mean a bushing is wearing down and you never even broke the seal on the gearbox to find out.
And ultrasonic acoustics, right? Hearing a bearing losing lubrication over the roar of a factory floor. You're basically giving machines a blood test and an MRI instead of doing exploratory surgery.
You completely eliminate the risk of introducing dirt or making a reassembly error.
But wait, my head gets stuck on one detail here. If we aren't using a calendar for the teardown, don't we still have to use a calendar to schedule the vibration reading?
Yes, the data collection is scheduled, but the interval of that schedule is dictated by physics, not a guess. This is based on the PF curve.
Let's break down the mechanics of the PF curve.
So imagine a graph mapping a machine's condition over time. P stands for potential failure. That's the exact moment a fault becomes detectable by a sensor. The oil shows metal or vibration spikes.
Okay, and F is functional failure, the moment it actually seizes up and dies.
Right. The time between point P and point F is your PF interval.
Let me walk through this to make sure I have it. Say a bearing starts spalling today, and my sensor detects it. That's point P. Based on the physics of that bearing, we know it takes roughly 3 months for the spalling to completely shatter it. Shattering's point F. So the PF interval is 3 months.
Precisely. And the golden rule is that your inspection interval must be significantly shorter than the PF interval.
So if it takes 3 months to die, you might schedule the vibration rad every month.
Exactly. A slow-developing fault gets checked less often. A fast-developing fault requires highly frequent monitoring. The schedule bends to the physics.
The machine dictates the terms. That's brilliant. But, I mean, let's be practical. If you have a massive food processing plant with thousands of tiny motors and pumps, you aren't putting a $5,000 sensor on a $50 fan.
No, of course not. That would just be replacing labor waste with capital waste. Mature plants use a deeply pragmatic hybrid model mapped in their CMMS. They triage their assets into 4 tiers.
How does the triage work? Who gets tier 1?
Tier 1 is high-cost or critical equipment. Main production drives, huge utility compressors, the bottleneck machines where downtime costs thousands a minute. These get the full predictive CBM treatment. Permanent sensors, monthly oil analysis, the works.
The VIP treatment, what's tier 2?
Safety and regulatory systems. Backup generators, fire pumps, relief valves, these stay on incredibly strict, non-negotiable, time-based schedules.
Because you do not wait for a fire pump to show degradation on a sensor.
Right. The consequence of failure is unacceptable. You test it on a calendar, period.
Never optimize away safety. Got it. Tier 3.
Consumables, things that actually follow a predictable wear-out curve. Filters, belts, oil changes. These stay time-based or usage-based because we know how they behave.
And finally, tier 4. Simple, low-cost equipment, fractional horsepower motors, hand tools, small exhaust fans. I'm guessing we just ignore them.
The official strategy is run to failure. You intentionally do nothing. Because paying a tech $70 an hour to take a vibration reading on a $200 motor every month is financial malpractice.
When it dies, you just throw it away and bolt a new one on. It's a calculated financial strategy, not negligence.
Exactly. So when a facility actually has the discipline to map this out, kill the useless PMs, and implement this hybrid model, the transformation is staggering.
What do the numbers look like?
They typically see a 20 to 40% absolute reduction in total PM task volume. They aren't working faster, they just eradicated the useless work.
And the culture shift on the floor has to be massive. Techs know when they're doing busy work.
Oh, totally. PM compliance, meaning tasks actually completed on time, often jumps from like 60% up to 90% or higher. The schedule is finally realistic.
It respects their intelligence.
And most importantly, plants go from spending 50% of their time fighting emergency breakdowns to operating at 85% planned, controlled work. They control their own destiny.
The goal was never less maintenance. The goal was maintenance that actually has a reason to exist.
You transition from measuring volume of effort to measuring the actual value of reliability.
This has been an incredibly eye-opening journey. Let's synthesize what we've uncovered. We dismantled the assumption that age equals failure, learning that 85% of equipment failures are entirely random.
We explored the terrifying reality of that infant mortality curve.
Right, realizing that intrusive maintenance actively introduces human error and causes the failures we fear. We walked through the no-fault repetition check. If your finding rate is under 2%, you are burning money.
And we saw how condition-based monitoring lets the machine dictate its own care.
It's a profound rethinking of how we interact with physical systems.
But as we look at the psychology behind the assumption factory, I think there is a deeply compelling application here that extends way beyond industrial engineering.
Oh, where do you see it connecting?
Well, we've spent this entire time discussing machines and factory schedules, but zoom out and look at your own professional life.
Oh boy.
Think about your daily workflows, your recurring weekly meetings, those status reports you generate every Friday. What recurring activity in your own daily operation survives purely because it has always existed?
Wow, the assumption factory is operating in my own calendar.
Exactly. If you took the no-fault repetition check and applied it to your own digital schedule, if you looked at a standing weekly meeting and asked, how many times in the last 6 months did this actually produce a critical finding or alter our behavior? How much of your own routine would turn out to be pure waste?
That is a phenomenal and honestly slightly terrifying question. Are you performing unnecessary intrusive maintenance on your own productivity? Are you holding on to habits that outlived their purpose years ago? That is a profound thought to sit with. Thank you for joining us on this deep dive into the hidden world of reliability. We encourage you to take 30 minutes this week to audit just one recurring task, whether it's a work order on your factory floor or a recurring block on your personal calendar. Apply the check. See what you find. Until next time, keep asking why.